Hey guys, so the last couple days we were going over some review of ionic compound stuff. Today we're going to start reviewing molecular compounds instead. So none of this should be new to you. We're just going to be going over how to write names and formulas of molecular compounds, but this is all just review of stuff that we did in Science 10. So we're going to be going over how to identify if something's a molecular compound, how to determine the bond capacity of different elements. We're going to draw some dot diagrams of molecular compounds. And then if you're given the name, how to write the formula. And if you're given the formula, how to write the name of these molecular compounds. So molecular compounds are compounds that form discrete molecules. So they don't do the whole crystal lattice thing that ionic compounds do. Instead, it's like an oxygen molecule and then another oxygen molecule. They're not all like connected to each other the way ionic compounds are. Molecular compounds are also called covalent compounds or covalent molecules because the bonds inside the molecules are covalent bonds. And by that, we mean that the bonds are formed between nonmetals and metals that are sharing electrons. So unlike ionic compounds, where you have ions form when one of the elements loses an electron and one of them gains an electron, there is no loss and gain of electrons with molecular compounds. It's all just sharing electrons in a bond. So because of that, molecular compounds are not made of ions. All of the atoms are neutral. Valence electrons, if you remember, are the electrons in the outermost shell of an atom, and you can determine that, especially for nonmetals, just based on what column of the periodic table they're in. Only lone electrons can be involved in a covalent bond. There is an exception to that, which we'll talk about in the next lesson, but that's the general rule. So when we're determining the bonding sites of an atom or an element, we're just looking at how many lone electrons it has. So carbon has 4 valence electrons, all 4 of them are by themselves, so it has a bond capacity of 4. Oxygen has 6 valence electrons, so 2 of those are in pairs, 2 of them are by themselves, so it has a bond capacity of 2. Okay, next we're going to look at how to draw some Lewis dot diagrams, which is essentially just draw out the valence electrons for all of the atoms and then connect them in a way that you end up with all of the lone electrons in a bond. The structural diagram is just another name for the kind of finished form of this. Just a reminder that you can have double and triple bonds between atoms where you have multiple pairs of electrons that are being shared between those two atoms. So a double bond has 2 pairs of electrons or 4 electrons in total. A triple bond would have 3 pairs of electrons for 6 electrons in total. A double bond is just represented by 2 lines. A triple bond would be 3 lines. Okay, so before we get on to naming, let's look at some examples of what these diagrams would look like. Okay, so for example, if we were going to draw a diagram for, let's say, nitrogen trifluoride, I would draw my nitrogen, which has 5 valence electrons because it's in the 15th column. And then my fluorines have 7 valence electrons because they're in the 17th column. And whichever atom has the most bonding sites, that's the one that you want to put in the middle. So nitrogen has 1, 2, 3 bonding sites. Fluorine only has 1 bonding site. That means our nitrogen should go in the middle. So I'm just going to put the fluorines with their 7 valence electrons around the outside, like so. My next step is something I like to call sausaging, and that is when you take the lone electrons from 2 different atoms and you sausage them into a bond together. Most things are going to be sausaged to that central atom. So I'm going to do it like that. And then the final step is actually drawing out what's called the structural diagram, which is just to represent each of these sausages or each of these bonds with a line, like so. And then you also do need to draw in any of the unbonded pairs of electrons that are around the central atom. You can also draw them around the other atoms, but you don't have to. You only have to draw them around the central atom. Okay, let's do another example that involves not only single bonds. So for this second example, I'm going to do, let's say, carbon bonded with oxygen. And you'll notice I didn't tell you how many of these you're going to need. So I'm going to start with a carbon, which being in the 14th column is going to have 4 valence electrons. Oxygen, being in the 16th column, is going to have 6. And so I have my carbon, I have my oxygen, I am going to sausage like so. Now you'll notice I still have 2 unbonded electrons around my carbon, and that cannot be. That means I have to add another carbon or another oxygen. Since oxygen needs 2 electrons, and that's what I have left here, it's going to be the simplest molecule if I add another oxygen, like so. This makes more sense because we have our carbon, which has 4 bonding sites, or a bond capacity of 4, is in the middle. Our oxygens, which only have a bond capacity of 2, are around the outside. And now to draw the structural diagram for this, I have the carbon in the middle. It has 1, 2, so a double bond to each oxygen. And so now I have my oxygen, my carbon, my oxygen, a double bond between each. And my central carbon atom has no pairs of electrons, so I don't have to draw any of them in. So that would be my final answer. Just so you guys know, on a test or quiz, this part is necessary. I would recommend, especially when you're getting started, to draw out your sausaging, but you don't need to do that. If you can, just do it in your head. And some of you will likely be able to start doing it just in your head as you get more familiar with this stuff. As one last practice question, I would like you guys to try drawing out the structural diagram for a molecule that includes both fluorine, carbon, and sulfur, and see if you can figure out how that would be arranged. I want the simplest molecule possible for this. So try it and then come back to the answer. Okay, so for this one, you should have started off by drawing your carbon in the middle, since it has 4 valence electrons and 4 bonding sites. Sulfur has 6 valence electrons, so 2 bonding sites, and fluorine has 7 valence electrons, so only 1 bonding site. You would then sausage between the fluorine and the carbon, and between the sulfur and the carbon, getting a double bond for that one. And you would realize that you still have 1 valence electron around the carbon that's just by itself. So the easiest thing to do would be to add another fluorine, which has a lone valence electron of its own, to create another carbon-fluorine bond. Your final answer should be a carbon with 2 single bonds going to 2 different fluorines and a double bond going to a sulfur. Okay, so next step, when it comes to naming molecular substances, unlike ionic compounds, with molecular substances, we use prefixes. And those prefixes go before the name of every element, and they tell us how many atoms of that element are in the molecule. So yeah, you do need to memorize all of these prefixes that are in this chart here. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. We don't use the prefix mono because that's the very beginning of a molecular compound's name, but you would use it before a second element's name. So yeah, for example, C2H4, dicarbon tetrahydride. If you had something like N5Cl7, what would that be? So for that, you should get pentanitride nitrogen heptachloride. So penta for 5, hepta for 7. Okay, and don't forget, just like with ionic compounds, we do change the ending to IDE. If you had something like, let's say P2, that would be diphosphorus. And then because we always change that into IDE, diphosphide, phosphide. The one thing you do have to watch out for is your Hofbrinkel or diatomic molecules. So that is hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. The Hofbrinkel molecules, they are also called the diatomic molecules. For those ones, if you're given, say, H2, that would just be hydrogen. You don't use prefixes, you don't change the ending. All it is the name of the element. So same with like N2 is just nitrogen. So that becomes really important because if I say I want you to react nitrogen with oxygen, I mean react N2 with O2, not react N with O. So anytime you see the names of diatomic molecules, you have to know that they come with a little 2 behind them. There are other molecular compound names that don't follow this kind of rule of using the prefixes. So water, you have to just know is H2O. Ammonia is another one you have to have memorized. It's NH3. Methane, you have to have memorized. It's CH4. Hydrogen sulfide, also called hydrosulfuric acid, is H2S. That one you don't have to memorize until the 3rd unit, but eventually you will. The other ones that are on this list you don't have to have memorized. Okay, so when it comes to molecular formulas, that is when we're given the name and have to figure out what the formula is. This is actually a lot easier than doing it with ionic compounds. If you remember with ionic compounds, you have to like cross your charges. You don't need to do that with most molecular compounds. Instead, the prefixes are going to tell you how many of each thing you need, so you don't have to cross the charges to figure that out. So yeah, so for example, if you have trinitrogen pentachloride, that's going to tell you that you have 3 nitrogen and 5 chlorine. If there's no prefix, you don't bother writing in a number because that means there's only one of them and we don't bother writing in ones. So let's give you an example of that to try. So if I said heptaphosphorus decasulfide, what would that look like? Well, because it's heptaphosphorus, that's 7 phosphorus, and sulfur is deca, so that's 10. And that's as straightforward as it is. So again, none of this should be new to you, but if you do have any questions about it, let me know. All of this naming stuff is going to become very, very important as we move into the next lessons, because when I give you an equation to balance or something like that, I'm probably not going to give you the formula. I'm probably just going to give you the name, which means in order to even start working on a question, you're going to have to be able to go from the name to the formula for both ionic and molecular compounds and your diatomic ones. Okay, so yeah, let me know if you have any questions about this stuff.